Hello and welcome to the afternoon session for the AnyLogic Conference. First up this afternoon is Cindy Ma from PricewaterhouseCoopers. Cindy will be speaking on scaling AnyLogic models for mass runs and sub-second responses. Cindy, thank you very much for being here. Looking forward to your presentation.
Thank you very much, David. All right, and thank you everyone for joining us for this presentation on scaling AnyLogic models. So as we all know, bigger is better, as evidenced by the ever-increasing sizes of phones. You can see from 2001 to 2022, the massive increase that we've experienced. Now, this is really bad news for the sewers of pockets, for example. As we can see, by 2030, the phones themselves will be larger than our human beings. Now, what does this mean, though, for AnyLogic? How do we sew ever bigger pockets for AnyLogic models? Well, firstly, we have to talk about what bigger means for simulation models. And over the years, we've found that largely this will fall into three cases. So that's what we'll run through today. The first case here is being able to do more runs. This we know mostly is present in our projects where we are doing scenario or policy analysis, especially for uncertain futures, of which there are a lot of them. And we have found that as we introduce scenarios and policies and bring our clients on the journey of exploring them with us, they become more and more sophisticated and ask for ever more scenarios and policies. And I should note here, when we say policies, we're really talking about the different ways that you can pull levers within a system to try to get the result that you want. Often we do this via optimization. Now, the second case is more users. Specifically here, we're talking about more concurrent users at the same time. And so a lot of organizations who are maybe putting their simulation models out there for a lot of users to use will experience this. A lot of people accessing the same model and expecting very good performance. For us, we're actually going to walk through a case today where end consumers are expecting to access a simulation model and run their own simulations in real time. And then finally, the last case is just when you have more model. Sometimes you just can't get around building a very detailed or very complex model, and there's just simply more models for you to build. And in this case, the approach really is to be able to optimize your code better and make better choices to try to make your model as efficient as possible. Now, to talk through these, we're going to actually use three examples today, three projects that we have done here at PwC. The first one is the one that shows more runs. And so this is a project that we did where our client needed to understand how the different blueprints that they were considering might impact how people use the office space, especially as we come back from the pandemic, and we have different hypotheses about how people might be coming in less now or might be working in more teams, and so a general change in people's behavior. So you can imagine that we'll want to run a lot of different scenarios here, as well as assess how each of the different floor plans being considered might work. So in this case, for us, the scaling needs are really that there are tens of thousands of runs that we might want to use. Likely the runs will increase actually over time, because as we explore with the client more, there are more questions that they have and will want to run more runs, still keeping the old ones. We'll want to iterate over the behavior. And so the number of runs actually increases during the course of the project. Now, it's likely that even though the number of runs is increasing, the time that you have to do each iteration doesn't increase. And so we needed to find a way to be able to scale our operations here. And then for the number of users in this case, it wasn't very demanding because this is a more traditional consulting project, and so we can just run it ourselves. We also don't need to do anything in real time per se. We can run this overnight and look at the analysis in the morning. In terms of the timeline here, we've included this so that we can see a little bit more context around the project. We did have a model that we started with and then built upon once we wanted to look at this specific pandemic use case. You see this little orange tab here, this will repeat on the next couple of slides, is when we feel we really managed to hit scaling. And so this is when some key change was made. And so in this case, it was when we wrapped it in a cloud pipeline for mass runs. Now that I've introduced the background, though, later on we'll go into exactly what we did to scale and what we found worked. Now, the second use case for more users, this is a calculator looking at retirement planning with a simulation sitting behind it that also models life events. And these can be stochastic life events or they can be planned life events. At the end of the day, the user wants to be able to put some input in and see what some planned, what trajectories that their retirement savings might go through. This is quite a different use case from the first one because you can see, firstly, any number of end users might be accessing this website at the same time, giving it input, expecting a simulation model to run, and then returning the outputs straight away. And this is part of a larger platform, in fact, where the rest of the website doesn't contain simulation modeling. And so the users will expect a similar kind of latency, whether they're looking at a web page or actually running a model. And so this one really did need to be very performance efficient. Yeah, and we already mentioned the large number of users. It does need to be online 24/7. Anybody can access this at any given point. The timeline for this, you'll notice, starts much earlier. So there was actually an ideation phase with an early model about a decade ago now, and then this was revamped in 2018, and then re-engineered to get some massive scaling effects. And then finally, now we've actually got an end-to-end model ops pipeline to maintain this particular example, because we need to include it in other components, but also be able to update the model with new data and with new functionality and push it through to the production platform that is up for everyone to use. Now, the last case, finally, is our more model case. This is a digital twin of a human body based on physiological science. This is obviously very complicated. There are a lot of components in this model. And so the focus here really is on being able to run everything very quickly without sacrificing the detail. The choices have already been made to make this as undetailed as possible. And this is as low as you can go. Now, another important thing to note here is that there is a lot of calibration that happens for a model like this. And so not only do you need it to be efficient while running to get results for an end user, this is another one that is exposed to end users who want to be able to put in input and get output straight away. So not only do you need to do that, you also need to be able to run calibration on this model and update it so that it is the most accurate model that you can have at any given point in time. And again, this one also needs to be online 24/7. Now, in terms of the timeline, this is yet another long project. You can see the first version started in 2013 until now. There is no orange dot on this one because it was more of a slow burn. There were small chunks were coded at a time. And so at every single point in time, we were trying to make sure that we were as efficient as possible. Now, those are the three use cases, three examples I want to use today for us to discuss how we did our scaling. So to summarize, though, the kind of quantifiable metrics about these three, that's what's sitting on the table here. We can actually elicit a bunch of criteria that we can now look at. And it's important for us to look at this when we start the project, when we start considering, oh, this might be a model that we might need to scale. So we ask ourselves these questions, and we ask ourselves these questions from the lens of what is acceptable. So not necessarily what is desirable. It would be great if I could run 1 million runs, but really what do I need as a baseline to be able to do? And so you can see that there is great diversity, even amongst just these three projects that we've chosen here, of course, for that reason. So how many runs do we need? In the more runs case, of course, a lot of runs, over 100,000 is what we ended up doing in each iteration towards the end of this project. For the retirement calculator financial wellness case, there is stochastic behavior in there. So we needed about 2,000 runs for everything presented to the user. And then for Bodylogical, it was between 1 and 1,000. There are multiple use cases in this. And this was a little bit of clever thinking, which I will jump into in about 2 slides' time. The second question that you want to ask yourself is how many users are going to need concurrent access? For office modeling, it was 1. Hundreds of thousands for financial wellness, and we were expecting fewer than 100 for each instance of the Bodylogical, for each installation of it. Again, we're looking at how much time. This is very important. So we could run this overnight, so it doesn't need to be that fast. Whereas these two models, we needed something to come back to the user basically straight away for financial wellness. And for Bodylogical, people were a little bit more patient. This was an enterprise use case, so not consumers sitting at the end directly. And then another important thing to consider is what are we doing with the output? Do we need to store this in the cloud, or do we need to send it straight back to a user via some sort of API? And then similarly, of course, we need to consider, do I need to stream input data in? And we're quite specific here with the stream because, of course, for models, you want to have input data, you need a way to be able to update your input, but do you need it to come in live? And so for financial wellness, this was yes. And in this case, it was because we can't hold on to any of the financial data, so it needs to be streamed into the model only for use during that period and then immediately destroyed afterwards. And then finally, there may be a lot of security restrictions. So this has been reduced down to this one row, but this is a huge question and a huge headache really for anyone working in a large organization. And so it's important to consider these at the beginning as well, and this will impact how you architect your solution. So let's now jump into what we did. So for the more runs case, you can see quite a simple architecture here. I will say this is where we ended up. Initially, we hadn't purchased and deployed AnyLogic Cloud yet. And so we were running everything locally. This was excruciatingly slow and really took up my laptop every night. And you would wake up in the morning and sometimes there would have been an error. So moving to the cloud was a huge relief here. So it doesn't lock up your laptop. So in this case, the architecture is quite simple. We had input data that's sitting, in our case, just in CSV files. This gets piped into a model. The model is then able to write to, in our case, we had blob storage set up. So directly write from something that's stored on cloud through to blob storage. And then there was also a Tableau server for visualization, as that is what our client team used. In this quite simple architecture, we learned a lot in implementing this, and definitely the moving to a cloud solution made things a lot more scalable because now you can throw resources at it if you need it to be faster. You can also run multiple scenarios in parallel so that you can see results rolling in all at once instead of having to wait for each scenario to finish as you might do locally. Now, major takeaways in this particular case was that you should always code well, right? In your model, you should always design your models well anyway. But for us, being able to reduce the more expensive transitions, because there were state charts in this particular model, was very important. If you're using SD components, then understanding exactly what granularity of time you need would also help speed it up. So being able to make those decisions, very important for a model like this. For us, we built and then tested locally and then scaled for use in the cloud. It sounds like with the direction that AL9 is going in, we'll be able to just build in the cloud directly. But for now, I guess, until next year, we'll still be planning to build and test locally and then deploy to the cloud. Now, prior to AnyLogic Cloud, this was quite manual. I would build it, I would export a jar, and then we would ship that over to a compute instance and then run it there. With AnyLogic Cloud, of course, I can just directly push that into the platform, and then it can be run actually by someone else to produce the output data. And so that is actually our last takeaway there. In terms of the skills required to implement this particular one, we found, so of course, you have your simulation modelers. You also need someone who is familiar with Python enough to do pipeline development in order to have the whole thing running end to end. And then we also needed, really, we have someone who's our expert on AnyLogic Cloud, Bamsi, who might be in the chat if you have any questions for him. So that was needed in order to get everything stood up here. And then finally, a dashboarder to finish off the project and provide some analysis. So this is the set of skills that was required to pull this particular case off. The second case for more users, this is a very, very simplified diagram of the architecture, but you can already see there are a lot more parts than the previous one. So to walk through it quickly, there is one data store so that the input and output data actually returns to it. And then the model code, so the AnyLogic model was packaged up as a jar, and then there was some more custom engineering done around that. So a larger program runs the model, controls inputs, parameters, and then also does everything in parallel, of course, to the extent that parallel runs were possible. And then there were larger model operations to connect this to a front end, which was the rest of the platform that we weren't quite responsible for. So there are lots of, I will actually talk about these in the takeaways right now, actually. So in this case, we did have to develop extensive pipelines because there was a lot of input and output data management. I mentioned briefly earlier. So in this case, the client held on to a lot of financial data. And in some of the particular use cases, we can't actually hold on to that data. So it doesn't sit in our data store. So this needed to be streamed into the model and then outputted, and then the model run, and then outputting only results, and all of that data gets destroyed. So this is all done via some custom engineering. There was a lot of code optimization there. And then another clever thing done here was that not all of the model needed to be in AnyLogic. So we would take out some of the components that maybe could run individually, and then have those just as Java code sitting outside. And then the custom engineering ran the particular components as needed. Another thing that was done here was that a lot of runs were pre-run and then stored in a data store. And then the user could also be matched to one that was in the data store. So a little bit of caching there so that you don't have to run everything from the beginning. In this case, of course, we have our simulation modelers as our skills needed, but really a lot of model operations engineers were used to pull this off. So to summarize, the key here was that the AnyLogic model was sitting in a jar file with a lot of custom engineering sitting around it in order to feed to a front-end FinWorld portal. And then this case also, everything was coded up so that you could access the model via an API. So it's all quite efficient for front-end developers. They don't need to deal with anything that they haven't done before, even though the simulation technology was new for them. And then finally, in case 3, so in this case, for the more model case where we were doing a digital twin of the human body, the architecture is quite simple. As displayed here, but again, useful tricks were done, so I'll walk through these. But in this case, quite simply, there was input data. This is updated very regularly. It runs through the model, we output data, and then this goes straight to a user interface. For this case, the two major challenges were the calibration. So a lot of the user data was frequently updated, and then there was also user data that a user would input the first time they logged into the platform. Now, the user isn't going to sit there while you wait, while you calibrate the model for thousands and thousands of runs. So what would actually happen was, in some of the use cases, we would identify using a machine learning model, k-nearest neighbors to be exact, which already pre-run data set was closest to the person using the model, and then present them the results there first, and then run a calibration for that individual with their individual data that they had given permission for now that they'd logged into the platform. That would be run overnight. And then the next time they logged into the platform, they would actually see their individually run data. And then also there was a lot of scenario analysis to do here too. And so after getting that data and calibrating the model for that individual person, all of those scenarios were also pre-run so that the next time they logged in, they could see those results straight away. Important to note here is that at its peak, and I will note that this also turned into a phone app, so it was much larger than our usual consulting project, but at its peak, this turned into a production team of 18. So there are a lot of developers working on this. And then, so in terms of the skills required, we have our simulation modelers, we have our web developers, and our iOS developers for the app, and then UI UX designers for the entire platform. Okay, so that's a quick run through of how we did all of our scaling. I did want to talk briefly now about what we think is next. So you might have noticed that for all of these cases today, the simulation is one part of it, but really it's sitting in a larger solution, whether that be for the first one, the framework with which we can do scenario analysis, or for the second one, it was sitting inside an entire larger portal that manages all kinds of financial wellness offerings. And then the last one being within a larger website and within an iOS. So all of these are broader solutions. And in order to do that, then we have to scale our models. And so it's good to think about that from the very beginning these days. Now, if we're doing solutions now outside of models, then of course there's going to be more documentation. So we spent a lot more time compared to before documenting. There were more individual pieces, and the integration points of pieces are very important to document. So we spent more and more time doing that. And then, of course, creating the systems of documentation and creating patterns that we can all follow does result in long-term benefits, so you can standardize this across teams. We did find that, or at least I did find that I had to pick up a lot of additional skills. So my Python definitely improved over the last couple of years, being able to code up pipelines for these mass runs, and then being able to, and then then we installed AnyLogic Cloud, of course. And so at that point, then I could separate again, and I could be responsible just for the modeling part and pushing the model up to the cloud. And then somebody else could hit that API, get the results they needed. So I think maybe we can say for smaller projects, for the prototyping phase, you can expect that you should expand your skill sets. Your simulation developers will need to expand your skill sets to be able to do a bit more of the pipeline. But once we do move to a cloud type solution and the model is more offered as an endpoint for an API, then you can once again have that abstraction, which is great because then it does allow us to exploit already established roles. Like a web developer does the web dev, doesn't have to learn too much about simulation, whereas I can just do a simulation. Because early on, when we did do a front-end web browser type application connecting to a Java model in the back end, there much more communication was needed. They needed to pick up new skills. I needed to pick up new skills. So having the AnyLogic cloud separation is really a good side bonus. And of course, this opens you up to new learning methods like RL, ML, which was talked about already. And then finally, I would say that we do expect to be delivering more integrated simulations in the future. So simulations become more native to a lot of applications. We expect they'll be more behind the scenes. A lot of people are thinking more in terms of scenarios now, we find, than before. And so they'll be expecting some sort of simulation model behind a polished web application, or maybe it's very summarized by the time it gets to the user, but we'll be providing more behind the scenes type analytics. And then and to do this, we find that they probably will need to happen in the cloud because a lot of the front ends will be provided in the cloud, and will need to be they will need to be done with good input-output performance. So just to wrap up, I know we're all waiting for these giant phones, but it turns out in order at least to deliver AnyLogic simulations, we probably don't need a giant phone. We can do it with a cloud platform, the obvious choice here being AnyLogic Cloud, at least it was for us, and then some clever configuration and some clever ideas about whether or not you can use hybrid models or cache some results. And with that, I think I can take any questions. Okay, so I have a question here. Isn't more concurrent users a problem for the web platform to solve rather than the sim? So yes, this probably is a lot also due to the conflation of our roles, but it does depend. So you can, of course, if you're packaging up the model, especially for an API, then it's going to be up to the web platform to do this. So before we were able to package it up like that, though, we did have to take care of a lot of that. It also, it's a team. So if we can get the model to run as quickly as possible, then the web people don't have to take as much of that load. Okay, and then second question. So for the second two examples, did you not use AL Cloud for? Yeah, so in short, they happened before we got AnyLogic Cloud. And then they're now big legacy systems. So we'll have to plan a big migration project to try to migrate those over if that's the way we go. Okay, and then third question, do you have any specific tips for code optimization within AnyLogic? I believe there is a lot of material out there for this. I've done most of my learning through experience. I will say that so we did a number of experiments ourselves, actually, just with testing with different components, with different numbers of agents, what we found to work the best. Especially for us, we needed to make sure our state charts work the best. But in terms of general tips that I've learned, a lot of the Java principles apply. So loops are slow. Try to nest as few loops as possible if you can, compile them into like lists and then loop them. If you're trying to retrieve objects from lists or other collections, use maps. Only use them if you need to iterate. So a lot of the general Java tips apply. Okay, and then next question. In the Bodylogical example, you mentioned having up to 18 people working on the project. What recommendations can you give us for having multiple people work in the same model? For example, did we at any point implement any type of Git technology? Yep, so some parts of that were outside of AnyLogic and some were within AnyLogic. So I'll try to break this into those two parts. So within AnyLogic, we have in the past tried to break up the parts of the model. So you can do this by like coding up separate models and then dragging them in as libraries. So you can have somebody working on a part that is basically a module that's then reusable by someone else. Still a lot of communication to be done there, which I guess is, that's the case for any of these projects with multiple people. So that is still a lot of work. That is one way we've dealt with that. And then outside of the model, then definitely we definitely use Git. Branching is very important. Versioning is very important. So in that case, it's mostly like there's a lot of code sitting outside of the model too, and we would also have the ALP file is sitting in the repo. Okay. I believe that those are all of the questions. So thank you everyone for joining me for this presentation. I hope it was useful.